Welcome to Keentel Engineering. Today, we are covering the electrical design engineering framework for a combined cycle power plant, a milestone-based process running 30% through 60, 90, and issued for construction. The site basis is 13.8 kilovolt medium voltage, 480 volt low voltage, and the USI EEE and ANSI framework. The Keentel position. Grid interconnection is a first-order design input, not a downstream utility formality. We anchor the interconnection basis at 30%. A combined cycle power plant pairs a gas turbine with a steam turbine, recovering exhaust heat through a heat recovery steam generator to reach 55 to 65% thermal efficiency versus 35 to 40% simple cycle with lower fuel burn, lower emissions, and fast start capability. 3 electrical systems interlock. Generation and interconnection covers generators, generator step-up transformers, and the switchyard tied to the transmission grid. Plant auxiliary power covers 13.8 kilovolt switchgear, feeding large motors, stepping to 480 volts for motor control centers and balance of plant loads. Emergency and control power covers 125 volt DC batteries and UPS that ride through a total blackout to protect rotating equipment. Interconnection requirements cascade backward into all 3. GSU impedance, generator capability curves, switchyard breaker ratings, auxiliary system survivability. Plants that treat interconnection as a late-stage checkbox routinely discover at 90% that equipment already procured cannot satisfy point of interconnection requirements. The reference architecture flows through 7 layers. Generators produce machine voltage at 11 to 24 kilovolts with their own excitation and protection packages. Generator step-up transformers, per IEEE, C57.12.00 step, that to transmission voltage for the switchyard and point of interconnection. The switchyard connects to the utility through HV breakers rated per IEEE 37.06. Unit auxiliary and station service transformers tap the generator bus or switchyard to feed the 13.8 kilovolt auxiliary system. Metal-clad arc-resistant medium voltage switchgear feeds the large plant loads, boiler feed water pumps, circulating water pumps, condensate pumps, and turbine skids. At 480 volts, switchgear and motor control centers serve motors under roughly 200 horsepower valve actuators and package skids. The 125 volt DC and UPS systems, sized per IEEE 485, provide protection, control, and emergency lube oil power. 5 energy flows tie the plant together: natural gas to the gas turbine, hot exhaust to the HRSG, the steam and feed water loop, cooling water between condenser and cooling tower, and electrical output from both generators to the grid. Every mechanical flow has an electrical consequence, most visibly in the large motor loads dominating the auxiliary load list. The standards basis is organized by system. Power system studies follow IEEE 399 and 551. Load flow, short circuit, motor starting. Protection and coordination follows IEEE 242, 3004.5, and the C37 series. Transformer design follows C57.1 2.00. Medium voltage switchgear follows C37.20.2 and C37.20.7, metal-clad and arc-resistant. Low voltage switchgear follows C37.13 and UL1558. Battery systems follow IEEE 485 and 946. Grounding follows IEEE 80 and 142. Step and touch limits E80 and 142. Step and touch limits, high resistance grounding. Arc flash follows IEEE 1584 and NFPA 70E. Interconnection and compliance fall under FERCLG IP and NERC MOD PRC and FAC. Model validation, ride-through, and facility ratings. The 30% milestone locks the project's most costly to reverse decisions. The scope, design basis covering voltage classes, grounding philosophy, and short circuit levels. The overall key one line showing generators, GSUS, switchyard, and UAT and SST scheme. A preliminary auxiliary load list with duty cycles and diversity factors, switchyard concept with bus arrangement and preliminary C37.06 breaker ratings, and the FERCLG IP interconnection data submission with preliminary power flow and short circuit models. Why is 30% the interconnection milestone? Every input the interconnection studies need. Generator reactive capability, GSU impedance, switchyard topology, auxiliary load at the point of interconnection is fixed at 30%. If those parameters change at 60 or 90%, the studies get rerun, the queue position may be at risk and the schedule absorbs the cost. At 60%, the architecture stops being conceptual. Equipment is sized and specified for procurement. Long lead packages must be technically complete because lead times drive the schedule. HV, MV, and LV1 lines are issued for design with ratings and impedances final. Medium and low voltage switchgear specifications go out for long lead procurement. GSU, UAT, and SST specifications follow. The first full load flow, short circuit and motor starting study pass is complete with equipment duties verified. Grounding and lightning design is developed from soil resistivity data. DC and UPS sizing is complete per IEEE 485. The protection philosophy is issued with relay functions and zone definitions. 60% is the last point at which technical parameters can change without direct cost and schedule impact to procurement. At 90%, the analytical work closes. Final power system studies run on as-purchased equipment data. Certified vendor test reports, not assumed values. Protection coordination produces complete time current curve sets and utility POI relaying. Arc flash analysis per IEEE 1584 produces incident energy values and the panel label schedule. NERC compliance covers PRC-019, PRC-024, MOD-025, MOD-026, MOD-027, and FAC-008. The final grounding grid demonstrates step and touch compliance. The 90% trap is the most common CCPP failure mode. Studies still running on assumed data when the milestone is declared. If coordination and arc flash are built on estimated impedances rather than factory test reports, the settings and labels issued at IFC are not valid, and the plant inherits the liability. Keentel gates the 90% studies on receipt of certified vendor data. IFC is not a drafting exercise. It is the point at which the engineer of record stakes a professional license on the package. Every review comment is closed, every calculation checked and signed. The stamped IFC package is the legal basis for construction. Final relay settings and time current coordination sets are issued. Protection as installed matches the coordination study. The calculation archive is the owner's record and the NERC audit evidence trail. Commissioning procedures define the safe, sequenced energization path and the MOD field testing protocol. Construction support runs through RFIs, field changes, and factory and site acceptance test witness. As-built and model handoff establish the operating baseline and keep future study models current. Power system studies are not a milestone deliverable. They run through all four, maturing in lockstep with data quality. Load flow covers concept scenarios at 30%, all operating cases at 60%, and closes on vendor data at IFC. Short circuit sets design levels at 30%, verifies equipment duties at 60%, and closes available interrupting current margins at IFC. Motor starting screens the largest motors at 30%, confirms 85% or better terminal voltage at 60%, and uses certified curves at IFC, with variable frequency drives where needed. Coordination starts as a philosophy at 30%, produces preliminary time current curves at 60%, and issues final curves with settings at IFC. Arc flash produces preliminary energies at 60% and final labels at IFC. Grounding runs soil resistivity at 30%, builds the grid model at 60%, and demonstrates step and touch compliance at 90%. Interconnection submits study data at 30%, absorbs results through 90%, and closes with compliance evidence and field tests at IFC. A real project. A 2x1 combined cycle plant, approximately 700 megawatt class, interconnecting to a 230 kilovolt transmission system. The challenge: GSU impedances and switchyard arrangement had been chosen for cost, with interconnection treated as a parallel track. Early cluster studies showed point of interconnection short circuit duty approaching breaker interrupting capability, and the reactive range required could not be delivered by the generator as configured. The approach: rebuilt the 30% basis with interconnection as a first-order input, re-optimized GSU impedance against both short-circuit and reactive transfer requirements, moved to a breaker-and-a-half switchyard arrangement, locked the LGIP submission as a controlled deliverable. The outcome: revised parameters passed the restudy without a queue position change. No interconnection-driven equipment change occurred after 30%. GSUs released for procurement at 60% against final study-consistent impedances. The project's independent engineer credited the integrated model with removing the largest single schedule risk. Common questions on combined cycle power plant electrical design: why deliver in 30, 60, 90, and IFC stages? Milestones create controlled decision gates. 30% locks costly to reverse decisions, 60% releases long lead procurement, 90% closes studies. IFC transfers a stamped package for construction. Why 13.8 kilovolts rather than 4.16 for medium voltage auxiliaries? 13.8 reduces feeder currents and cable quantities for large loads. 4.16 remains attractive where motors cluster in the 250 to 3,000 horsepower range. What does high-resistance grounding buy on the medium voltage system? It limits ground fault current to a few amps, letting the plant ride through a single fault without an immediate trip. A significant availability benefit. What drives GSU and UAT sizing? The GSU is sized for the generator's full megavolt amperes at rated power factor, impedance balanced against point of interconnection short circuit and reactive transfer requirements. The UAT is sized for worst-case simultaneous auxiliary demand. Where do motor starting problems usually show up? Boiler feed water pumps are almost always the binding case. IEEE guidance requires 85% or better terminal voltage during acceleration. Who should do the interconnection engineering? The work products are inseparable from plant design. Splitting them creates interface risk that surfaces at energization instead of 30%. Let's close out on why combined cycle plant design has to be interconnection first. The point of interconnection isn't a downstream utility formality. Its requirements cascade backward into GSU impedance, generator capability curves, and switchyard breaker ratings. That's why the interconnection basis gets anchored at 30%, with the LGIP data submission treated as a controlled deliverable with the same rigor as the one-line diagram itself. At 60%, the long lead procurement releases, GSU, station service transformers, and medium voltage switchgear specs go out for order because transformer lead times are what actually drive the schedule. 90% is where the studies have to close on real certified vendor data. A coordination study or arc flash analysis built on assumed transformer impedances is fiction, and the plant inherits that liability at commissioning. A few details matter enormously along the way. High-resistance grounding on the auxiliary bus lets a first ground fault alarm instead of forcing a trip, which is a real availability win on continuous process equipment. And boiler feed pump motor starting is almost always the binding case for terminal voltage, which is exactly why many modern plants adopt VFDs. None of this works if NERC compliance is treated as an afterthought either. Excitation coordination, ride-through, and facility ratings have to be 90% deliverables, not commissioning surprises. If your CCPP project needs integrated interconnection and electrical design, Keentel Engineering can help. Visit KeentelEngineering.com. Thanks for watching.